So for the rest of this lesson, we're going to be focusing on when two functions are actually equal to each other or not. And there's two main conditions that need to be met for this to happen. So two functions, f and g, are equal if, first, they have the same domain. Okay? So if one of them has all real numbers domain, the other one must have that. If one of them has the domain x greater than or equal to 2, then the other one must also have that same domain. And then second, f of a equals g of a for all inputs a in the domain. And that's math symbol, so it takes a little bit of time for you to think about it. Remember, this means output and that means output. So we just mean they have the same output as each other. And if I put it in like simpler terms, what it means is a given input produces the same output into both functions. So if I plug a number into one function and into the other, they better give the same output if they're going to be equal, right? So let's actually do a check on some various functions that may or may not look equal and decide if they're equal, and if not, we'll tweak them a little bit. So for our next round of examples, here are the instructions. Make sure this is clearly written because actually this is very important. So we want to answer the main question, are the functions equal? That's the main thing. And in order to actually check that, there's a couple ways you could do. You could first just plug in numbers and see if they give the same output, right? Or sometimes you can just simplify and see that one of them is identical to the other completely, right? If they aren't equal, restrict the domain of one of them to make them equal. So every pair I give you here, if it's not exactly equal, it will be able to be at least equal sometimes. So here's what I want you to do. Take a look at A and B on your own real quick right now and pause the video and try to figure out for each of these if they're equal or not and finish following the instructions. And then we'll take a look together and then we'll do some more in-depth ones all together. So let's take a look at these together now that you've thought through it a little bit. Hopefully for A, you can see that by simplifying, they're actually completely identical. And so the answer for this is yes, they are equal functions already. Now, it's important to note here, these two functions, they involve a completely different sequence of steps though, even though they always give the same output. We've already learned that we can algebraically show this, but I want to remind you guys, if you just think of a number, like let's say 5. If I plug 5 in here, this is saying take 5 and multiply it by 6. So this function is saying 5 times 6, a number times the next number up. This function is saying take a number and square it, and then add the number to it, add that number you started with. Totally different sequence of steps involved there, but it's really cool how these two actually are completely identical. So using algebra can let us know that they're identical, and we just simplified to show that. But this does not allow us to use algebra, in which case it would be helpful to plug in some numbers. Now hopefully you tried some numbers out. I chose a number that provided a problem, or produced a problem. If you plug -4 for f, remember, in this case the order is different, even though it's got the same kinds of steps. This one has absolute value at the very end. This one has absolute value first on the input before you do anything, right? So this becomes +4 times 3 plus 2 and gives me 14. This though becomes -12 plus 2 first, and -12 plus 2 is -10, and then the absolute value becomes +10. They're clearly not the same function. So the answer is no, they're not the same function, but if you play with this enough, you'll realize the numbers that make the problem here has to do with what we know about absolute value, and that would be negative numbers. As soon as you plug in 0 or any number bigger than 0, you'll notice that this 3 times 0 plus 2 is 2, and then same here, they give me 2. So the key thing here is negatives made a problem. So how would we restrict the domain? If we make it non-negative numbers, so anything 0 and higher, now the functions are the same, okay? So, clearly these have a different order of their steps, But if we restrict it to x greater than or equal to 0, those two functions actually now have become identical. So it's not just the definition itself here in the function rule. The domain is part of a function's definition, and that helps us to answer these questions. Let's jump right into our next two. So the first function given here, you'll notice the difference between the two. Wait, we're bringing something back. This is a recursive definition here, and this is a regular closed form definition. We're just going to do this one together. You'll notice that if we were to build an input-output table for these, we're familiar with this, so we know 0 gives me 4, and here if you plug 0 in, it also gives me 4. And 1 gives me 9. Remember, this says take your previous input and add 5, so add 5. But if you plug 1 in here, 5 times 1 plus 4 is 9. So they actually, if you were to keep building this table, they give the same inputs and outputs as each other. But there's something very particular we need to remember. Recursive definitions are only defined on a domain that involves whole numbers. So actually, they are not the same because g of x has only, I will say, allows only whole number inputs. Okay, allows only whole number inputs. Okay, so we've learned that before. And f of x doesn't have to be whole numbers because look, plug in like 1.5. You can certainly plug that in and calculate. But 1.5 doesn't make sense here because this is always specifically referring to previous input, previous output. It's like a sequential ordering. It's like first, second, third, fourth, fifth, etc. We don't really do that with decimals and stuff, right? So which one of these would we restrict? We could restrict f of x to only whole numbers. Okay? So that would be the full answer to something like this. These are the same, but they're only the same if our inputs we're using are whole numbers. So we'd have to restrict this one to only allow whole numbers if they're going to be exactly identical. They do line up with each other very well. It's just this one has fewer numbers that you can actually do with it. But that's true of every recursive. So I wanted to bring this back because it is something that recursive are so useful in many ways, but they're only useful for things that are countable with whole numbers. Okay? So that's a cool one that applies to what we're doing. Here's another one where simplifying will be helpful. These two look way different to than each other, don't they? But watch what happens with g of x here. Now, first of all, you probably recognize right away that the answer to these being the same is no, or maybe. But if you watch something here, we can actually factor out, I didn't leave myself very much space here, 2x from the top, and it leaves me with x minus 7. So this is the same as that, and then my bottom is still x minus 7. Now, algebraically, we know, or I guess numerically I should say, we know that if you have something that's the same factor on top and bottom, that they can cancel out. And so you can say that this equals 2x because this cancels out. But there's a small thing here in math actually. The original function needs to still involve whatever problems, it needs to take its baggage with it, right? And it's carrying some baggage because we know this is a fraction, and we've talked previously what numbers are not allowable in a fraction in the bottom. We cannot have 0, right? What x value makes 0 here? Oh, 7. So actually, it's only equal to 2x, it turns out, but we still have to say, what I'm going to say is as long as x doesn't equal 7. Okay? So technically speaking, they are identical to each other because we simplified this one and we showed that it equals 2x. But he has to carry his baggage along with him. So he's only equal to 2x. As long as x is not equal to 7, then they're entirely equal to each other otherwise. Okay, so our last one of these is actually pretty important because this is looking ahead to our next major topic we're going to be studying after this unit we're doing right now. Now, let's just look at these together. And I'm not going to make you plug in or simplify right now to show that these are or aren't equal. I'll bet you can look at these and just tell, even if you did simplify, that they're not equal, right? However, they do have a part of each other that is equal. This is just 2x plus 1. He's a linear polynomial, right? Well, this also involves 2x plus 1, but it has a bunch of extra stuff with it. And there's no, like, it's not a fraction. You can't, like, simplify and cancel or anything like that. In fact, this, if you were to multiply it all out, this piece of it in normal form, you can see that it has x, x, x. It would be a cubic. It would be x cubed somehow, right? So clearly, this is cubic and this is linear. They're not equal to each other. So right away, we can say straight up, no, they're not. But let's go ahead and think about something. This thing is structured right here in a way that we've seen recently. If you have it in factors, there are some specific numbers that we can plug in for x that make this all just be 0. So if you can imagine with me here, you probably realize that if this was all gone, they would be identical functions, wouldn't they? Well, there are exactly 3 numbers that will make this all gone, right? For g of x, and then f of x and g of x would technically be identical functions, but only for those 3 inputs. There's only 3 inputs in this case that they would ever be able to be equal to each other, which is kind of interesting. But what are those 3 inputs that make this become 0? X equals 2, x equals negative 3, and x equals negative 8, right? So we should restrict to x equals 2, x equals negative 3, and x equals negative 8. And I'm going to say only, like we're saying those are the only allowable inputs, okay? And if we do that, then the 2 functions are the same. Okay, so I'm going to say then f of x equals g of x. And that might seem silly, there's only 3 numbers that work, but there's a lot of mathematics behind the scenes here that provide, that's really important to understand as we move on to things in the future. Okay, so these are definitely not the same. However, if we were to restrict it specifically to x equals 2, negative 3, and negative 8, then it turns out these 2 are exactly identical to each other. Let's take a look at this one just a little bit deeper, and then we have one last thing to get to. So here are the graphs of the 2 functions we just looked at. F of x equals 2x plus 1 is just like we know. It's a linear function. And then this one is 2x plus 1 plus all this other stuff. And we already talked about how this is cubic. So clearly they're not the same function. In fact, you can just look at the graphs and it's very clear that they're not. But what we just figured out, if you remember, we restricted the domain to specific values. And what were those values? Look where these 2 graphs cross. What that means is this is where the 2 functions are exactly identical, and everywhere else they're not identical. At negative 8, negative 3, and positive 2. So that's a really cool visual representation. So obviously they're not the same function, but we sort of forced them to be the same function just at those 3 points. What we really did was found where those graphs intersect. So to wrap things up, we're going to look at some weird functions. Let's start with this one. F of xy, wait a minute, 2 inputs. Yeah, this actually takes coordinate pairs as inputs. And then the output is actually calculated by 3x plus 8y. So that actually spits out just one number, because whatever these 2 numbers are, when you do this calculation, it actually puts them together into just one single number. So our domain is all ordered pairs, x, y, but our range is just single numbers. And in this case, this would actually be all real numbers. And this x and y are also both allowable to be all real numbers, because there's no problem in that calculation, right? So for example, if I started with the input negative 3, 1, what would that match with over here in the range? Well, if you do the calculation, negative 3 times 3 is negative 9, plus 8 times 1, so this actually gives negative 1. Now interestingly, it may be possible that there's another ordered pair that gives me negative 1. An example of a coordinate pair that would also give negative 1 would be 5, negative 2. If I plug 5 in here, 3 times 5 is 15, and negative 2 times 8 is negative 16, and 15 minus 16 gives me negative 1. So it's possible that multiple different coordinate pairs give the same output, but also we could have weird numbers in here, like square root of 2, comma 1.37 or something like that. And whatever that is, he's going to have a match over here. So any possibility of pair of numbers you can make a coordinate pair with is in the domain. And then all the single numbers that exist, just so you know, we won't prove this right now, but any number you could think of, you could figure out a way to get it, actually, by figuring out an x and a y. So this is a weird function, and it just shows us that functions are not just restricted to one number as an input and one number as an output. There's lots of different functions that exist for various reasons. So this is just something to get your mind thinking about. Now, functions don't even have to involve numbers at all, to be honest with you, because really a function is just simply a rule. And if you remember back to Algebra 1, a function just means if you put an input in, it just only has one output. It's okay if two different inputs give the same output, but if you put something in, it has a very clear output, right? So here's one. G of x equals middle name of person x. Now, if you're like me, I have two middle names. So maybe we'll just include names, and then that'll make it so it's, otherwise you'd be like, wait a minute, well, which middle name is it, right? You might also think, well, some people have no middle name. So what would happen with that? Let's draw another potato arrow diagram and just talk about this for a moment. So taking a look at this, our domain, meaning our inputs, that's people with middle names. Now, I say that because some people don't have middle names. I have an old student of mine when I used to live in China, and Chinese people generally don't have a middle name. And so if I were to put his name, Louis, he wouldn't have a match, right? So he's not really part of the domain. So it's only people with middle names. And the range would be all possible middle names. Now, when I say possible, there are some middle names that aren't possible, right? I'm sure there's some word or some name that exists that you could make up that nobody's middle name is that thing, right? So if we're talking domain and range, we have to be very specific, okay? And even in this, we could evaluate it. If I said G of Mr. Ingle, that equals James Christian, because that's my middle name, or my middle names. So there's just some examples of some other functions, and just to broaden your mind and make you remember that functions have a lot more going on than we might think they do. So that'll do for our lesson for today. Happy math, and we will see you next time.